All right, today we're going to talk about multiplying matrices, section 4.2. What did we talk about yesterday?
We did this a little bit yesterday.
Adding and subtracting. Yesterday we talked about scalar multiplication. Today we're talking about multiplying matrice to matrice, or matrix to matrix. So, first thing here, use the dimensions to decide whether matrices can be multiplied. So yesterday we talked about dimensions. In order to multiply two matrices, the number of columns in A must equal the number of columns in B. What this means is, let's say A were a 3 by 2 matrix. B would then have to be a 2 by 2 matrix. In order for us to multiply matrices, these two numbers must be the exact same. And why that is, we're going to see here in a bit when we actually multiply some. But in order to multiply, those two numbers have to be the same, and my resulting matrix is then the first row and the second column, or the rows of the first matrix and the columns of the second matrix. So my resulting matrix, for example, would be a 3 by 2 matrix. Same thing here. Could I multiply, let's say, a 2 by 4 and a 4 by 1? These are the same. My resulting matrix would be then a 2 by 1. If they are different, like we're going to see here in a bit, to determine which products are defined, check the dimensions as we just stated. For example, I can multiply A times B because they are the same. I can even multiply B times C because they are the same. But my question is, could I multiply A times C? No, because I have a 2 by 3 and a 2 by 2. I cannot multiply them because those two are not the same. However, let's flip it around. Could I multiply C times A? What's the dimensions of C? 2 by 2. What's the dimensions of A? Can I multiply C times A? Yes, I can. And my resulting matrix would be a 2 by 3 there. So this leads us into, you guys remember what the commutative property is? What's the commutative property state? It can be flipped around, right? Like when we talk about numbers like addition is commutative, like 2 plus 3 is the same thing as 3 plus 2. Multiplying technically is commutative, like 3 times 2 is the same thing as 2 times 3, right? However, with matrices are not commutative with respect to multiplication. So when you multiply one way is not the same thing if you were to reflip them and multiply again. They are different. So again, matrix multiplication is not commutative. If we have a problem like this, so for example here we talked about AC, on an assignment you would just say state not possible or undefined. Okay. So let's do a couple of problems here. Use the following matrices for exercises 1 through 3. Tell whether each product is defined. If so, give its dimensions. So first one, A times B. What are the dimensions of A? 2 by 2. What are the dimensions of B? Are they the same? Or can I multiply them?
Yeah.
And what's my resulting matrix going to be? 2 by 1. 2, I have BC. What are the dimensions of B? B is a 2 by, and what is C? A 1 by 2. Are these the same?
Yeah.
So can I multiply them? Yes. And what's my resulting matrix going to be? 2 by 2. And lastly, I have AC. What's the matrix of A? The matrix of C. Can I multiply these? No. So I'm done. Now let's talk about actually multiplying some matrices. To find a matrix product, what does the word product mean again? Multiplication. First, make sure the product is defined. So the first thing we got to do is find out, hey, what type of matrix we're going to have. What are the dimensions of A? It's a 2 by 3. What are the dimensions of B?
3 by 2.
A 3 by 2. Can I multiply those? And what am I going to get left over? I'm going to get a 2 by 2 matrix. Now, here's why those two numbers have to be the same. In a matrix, it's always what first by what. Like when I say 2 by 3, what does the 2 represent? What does the 3 represent? It's always rows by columns. Okay. Well, in order for us to multiply it, what I'm going to do is I'm going to take the row of the first matrix times the column of the second matrix. Again, I'm taking the row of the first matrix times the column of the second matrix. So I'm going to take 3 times 1, 5 times negative 1, and 1 times 0. And then I add those numbers up. So for example, here, let's do it again. 3 times 1 gets me 5 times negative 1 gets me, and 1 times 0. And I add those up and I get negative 2. That's the first location. Now, why does that make sense? Well, yesterday we talked about entries, right? What is the first location called? That's entry 1, 1. What does the 1 and the 1 represent? Row 1, column 1. So how do I get this number? By multiplying the first row by the first column. Same thing with matrices here. Next spot was A sub 1, 2. How would I get that spot? First row times the second column. And then they do the next one. A2, 1. Second row, first column. And then I have A sub 2, 2, which is?
Second row, second column.
Very good. So I'm going to do the next one here. 3, 5, 1, and 2, 4, 3. 3 times 2 is? 5 times 4. And 1 times 3. 6 plus 20 plus 3? 29. Next one. Negative 2, 0, negative 1, 1, negative 1, and 0. What's negative 2 times 1? 0 times negative 1. And negative 1 times 0. Add those up and I get? And lastly, negative 2, 0, negative 1, and 2, 4, 3. So second row, second column. Negative 2 times 2. Negative 4. 0 times 4. And negative 1 times 3. Add those up and I get? So my resulting matrix is negative 2, 29, negative 2, 7.
So it's not that hard, it's just a lot of work.
It is not the hardest. It is just kind of a lot of work, just like that. Okay? Smaller matrices are easier to multiply. Why? Because there's less to multiply and add in between. Bigger matrices, probably going to have to do a little more work with it. Again, after this, we see like 2 by 2s or 2 by 3s, 3 by 2s, something like this. That's pretty easy to multiply in your head. Okay, because you can multiply and add in your head and keep it all pretty straight. When you get some longer ones, yeah, it does get a little bit tougher. Let's try number 4. Number 4 is a great one here. What are the dimensions of the first matrix here? This is a 2 by 1. What are the dimensions of the second matrix? Can I multiply those? And what's my resulting matrix going to be? So my answer should be a 2 by 2 matrix. So notice that's 2 by 2. So I'm going to do the first row by the first column. What's 3 times 4? Awesome. Nothing to add there. Then I do the first row times the second column. What's 3 times 3? And then I do the second row in the first column. What's 1 times 4? And then I do the second row in the second column. What's 1 times 3? 3. My resulting matrix would be 12, 9, 4, 3. Let's try 5. What are the dimensions of the first matrix?
2 by 2.
And the dimensions of the second matrix?
2 by 2.
Can I multiply them?
Yep.
And what's my resulting matrix going to be?
2 by 2.
Awesome. And again, to multiply them, I'm going to start off with the first row and the first column. What's negative 1 times 1?
1. Or negative 1.
And 0 times negative 4?
0.
Negative 1 plus 0 is? Negative 1. Then we do the next one. First row, second column. What's negative 1 times 2? 0 times 0? Negative 2 plus 0 is negative 2. Now I'm going to go to the second row, first column. 3 times 1. Negative 2 times negative 4. 3 plus 8 is 11. And then I'm going to do the second row, second column. 3 times 2. 6. Negative 2 times 0. 6 plus 0 is? And I get my resulting matrix, negative 1, negative 2, 11, and 6. Questions? All right, let's move on to the next one here. You guys want to try 6 together with me? Let's look at it here. What are the dimensions of the first matrix going to be? 2 by 2. What are the dimensions of the second matrix?
2 by 2.
So can I multiply these? And what's my resulting matrix going to be? Awesome. So let's work this out here. What's negative 5 plus 0? 0. Right?
Multiplying, right?
Plus 0.
Negative 5 times 0.
Oh, you said plus.
Oh, sorry. Negative 5 times 0 is 0. Plus 2 times negative 1. 0 plus negative 2 is? So the first one is negative 2. Then I'm going to do the first row times the second column. Negative 5 times 4. Plus 2 times 2. Negative 20 plus 4 is? Negative 16. Now I'm going to do second row, first column. 0 times 0. Plus negative 3 times negative 1. 0 plus 3 is? And lastly, 0 times 4. Plus negative 3 times 2. 0 plus negative 6 is? Negative 6. So I have negative 2, negative 16, 3, and negative 6. Very good. Next one. I love a question like this. It gives me one matrix. It's A. It says A is 2, 0, 1, 3. It wants me to do A squared. What does it mean to be squared? Times itself. So I'm not just going to square each number. No, I'm actually going to take A times A. Or essentially the matrix of A times the matrix of A. So I'm going to do 2, 0, 1, 3 times 2, 0, 1, 3. So again, taking the rows times the column. Rows times the columns. Okay. Take about a minute or two, work these out on your own. All right, looking through this here. First row, first column. 2 times 2 was 4. 0 times 1 was 4 plus 0 is 4. Second column, 2 times 0, or first row, second column, 2 times 0 is 0 times 3. 0 plus 0 is 0. And then I did 1 times 2. 2. 3 times 1. 2 plus 3 is 5. And lastly, 1 times 0 is 3 times 3. 0 plus 9 is? Your resultant matrix will be 4, 0, 5, 9. Very good. Last one here. A and C. What are the dimensions of A? What are the dimensions of C? Can I multiply these? And what is my resultant matrix going to be? My resultant matrix is going to be a 2 by 4. Take a couple moments here, work this out on your own or with a partner. Let's go through the answers here. So the work. First off, 2 times 8 is 0 times 0. So 16 plus 0 was 16. 2 times 1? 0 times 2? So that gets me 2. 2 times 0? 0 times 3? 0 plus 0 is 0. 2 times 1? 2. 0 times 1? 2 plus 0 is? So that's the first row. Now I do the second row times each column. 1 times 8? 3 times 0? 8 plus 0 is? 1 times 1? 3 times 2? 1 plus 6 is? 7.
Wait, go slow on this one.
1 times 0? 3 times 3? 0 plus 9? 9. And the last one. 1 times 1? 3 times 1? 1 plus 3 is? And there's your resulting final matrix, the 2x4, 16, 2, 0, 8, 7, 9, 4. Awesome.
It's not too bad, it's just a lot to think about.
It is not too bad, a lot to think about. And here's your assignment.